Great to have you all here today. Welcome to JuliaCon, Pittsburgh. It's good to be here. My name is Matt Bauman. I've been a part of the Julia project a long time. Got involved maybe in 2013 while I was doing my grad degree here at Pitt. And so I was in Pittsburgh from 2010 through 2016 doing work in biomedical engineering. So it's really great to be back. What are you doing here? Well, welcome to everybody here. We um we hope that everyone here will be able to get started with Julia and kick off a good week. Ethan, you want to say something about yourself?
Yeah,
Come to the mic.
my name is Ethan Meitz. I'm a PhD student in the mechanical engineering department here. I'm part of the local organizing committee, and I've been using Julia throughout my PhD to do most of my research codes.
Hello, I'm Letícia. I'm a PhD student at CMU in the chemistry department. I have been using Julia since 2019, 2020. Uh, and I use it as a side project for my research and to develop codes for quantum chemistry and modeling in electronic structure of molecules and atoms.
Okay, so I'm going to walk us through the setup. So if you have your laptop here, great, take it out. We're going to walk through installing Julia, setting up the VS Code environment that we're going to need for the rest of today's introduction to Julia. So I guess I'll go through the outline very quick. So we're going to do just installing Julia, using VS Code, using the REPL in Julia. And then Matt and Letícia are going to guide us on a quote unquote walking tour of Julia. So we're going to go through some of the key points. And if you have questions about anything that we talk about, feel free to raise your hand. We can kind of take the discussion in whichever direction you guys think is important or what you're curious about learning today. So the high level things we have planned today is package management using the package ecosystem and package manager in Julia, basics of data wrangling and plotting in Julia, since Julia is a very strong at numerical computing. And then if we have time, we're going to talk about creating a package and deploying it to the general registry for other people to use. And then there's no scheduled break on the schedule, but around 10:30, which is maybe halfway through this, we're just going to take a break from presenting. You guys can go get coffee, water, stretch your legs, whatever. So to install Julia, if you've not done this before, you can go to this link here on the whiteboard, or you can go to Julia up on GitHub. So this link here is going to just show you these two install commands. These will install Julia up, which is the Julia manager for your system. This will allow you to install different versions of Julia, update your Julia, get like pre-releases, release candidates, that kind of thing. And it makes it really easy to kind of switch between different versions of Julia. I'm going to click through these slides. We'll come back to this at the end to make sure that everyone has their environment set up before we go. But while you're installing it, I'm going to spend some time motivating Julia as well.
So if anyone has trouble as you're installing things, raise your hand. Letícia and I can come sit next to you while Ethan's talking. Even help do skip setup here. Yeah.
Stupid question. What wireless?
Oh, that's the Pitt guest network. You should be able to log on. It'll take you to a web page. You agree to whatever their terms are, and it should let you in. And then the other thing we're going to need today is VS Code with the Julia language extension. So if you just go to the extensions in VS Code and search Julia, it should be the first one, and it will look like that. I will come back to the slide at the end again. But while we're all installing, I want to motivate a little bit about why you should use Julia. Some of you, I'm assuming, have used Julia before and just want to learn a little bit more, or maybe you're completely new to the language. So we're going to go over some of the common arguments that people make as to why you should use Julia in your research, in your work, for kind of hobby programming. The first one that I always hear is that Julia is fast. You can get performance on par with C or Fortran, but in the package of a high-level programming language. So the syntax of Julia is very similar to MATLAB or Python. It's very readable. It reads just like English, but it has the performance of C and Fortran. So this is some benchmark data here from the Julia Lang website comparing Julia here to a baseline against C and various other different programming languages like Rust, Fortran, Java. I believe Matt knows more about the benchmark details if you have specific questions. But the kind of key takeaway here is that Julia is much faster than most of these other languages. And I don't think anything specific was done to really try to optimize or fully tune this benchmark example for Julia. The next common important thing with Julia is that it's extremely composable. One of the key patterns in Julia is called multiple dispatch, which makes it very easy for packages to reuse and extend code from other packages. Something that's incredibly important in my research is using GPUs to accelerate the computations. In Julia, that's as easy as just changing the data type that I store my data in. So I switch from a Julia base array, which is just the array on the CPU, to a Julia GPU array. And when I call the matrix multiply function with a CPU array or a GPU array, it's going to dispatch to different backend code. One will run on the CPU and one will run on the GPU. And it's just as easy as that. All you have to do is change the data type. And this makes it really easy to write clean code or to change the behavior of your code without changing a lot of lines. Then also something that's really important is Julia is a relatively new language. There's many other libraries already written in C, Fortran, especially in the scientific communities, as well as libraries in Python and R and MATLAB. And Julia natively interoperates with C and Fortran. You can just call a C library directly from Julia, and there are packages to interoperate with Python and R and as well MATLAB, I believe. I think there's a talk on most of these later in the conference if you're interested. Another reason is Julia's package ecosystem is incredibly rich. A lot of the people that use Julia actually contribute packages to it. I know I have created a couple packages for my research. I've highlighted here a couple of the different GitHub organizations that I tend to use in my research. So there's the Julia plots, there's Julia GPU, which has backends for AMD, NVIDIA, One API, Metal, all of the different GPU vendors you can just use as an array programming interface. The Julia Automatic Differentiation organization, Julia Graphs, parallel programming, molecular simulation, and then the Julia Interop, which is home to all those packages that let you call things like C++ and Python. And then finally, another really strong component of Julia is the community. The Slack and Discourse are wonderful places to go and meet people and also get your questions answered. Very seldom will you have to wait much more than an hour to have your question answered by someone who is a domain expert or who maybe even wrote the package that you're asking a question about. Furthermore, literally every talk from most of the JuliaCons is on their YouTube channel. So if there's a talk that you missed at this conference or you were curious about from a different conference, that is on YouTube for you to go watch. And there are many, many more reasons that I did not talk about for time reasons, but there's a nice, it's called a manifesto on GitHub that explains more in depth why Julia is a good programming language and why you should consider it for use, for your use. Okay. So where are we with installing things? Does everyone have Julia and VS Code installed on their computers? Okay. Okay. Yeah. So yeah. Oh no. Yeah. I was just in VS Code. So we need to also make sure we have this extension. I see the slides did not update here, but that's okay. We do not need, there is not a GitHub repo that we're using. Matt is going to talk about his code later. So just make sure that you have the Julia extension. And once you have VS Code, please create a file in VS Code and name it with the .jl extension. Yeah, we'll just delete that. Oh, well, that's bizarre. Okay. Okay, so the last thing that I'm going to talk about today is the Julia REPL. Most of the code we're going to be writing today is going to be in a Julia file, but the Julia REPL is an incredibly powerful way to test and prototype your ideas as well. This is similar to the Python REPL, but in my opinion is much more powerful, and that is because it has several different modes. So the default mode is just it's called the Julian mode. It's just the one you can write and execute code. That's what you would expect. But there is also a mode accessed with the question mark, which lets you access the documentation for any variable or class or function that is currently present in your environment. So you can type question mark and then like cosine, and it'll print out the documentation for cosine. It'll tell you how to use that function. So it's really helpful. I use this more often than just going to the internet and trying to find the documentation. And then the other most important one is the package manager. You access this by pressing the bracket. This will change the mode to this kind of blue text here, and it will show your currently active environment. And this will allow you to install packages, update packages, manage your environment, switch to a different environment, and things like that. And I believe we will talk a little bit more about this later in the talk. So with that, I think Matt is up next.
Great. Well, thank you, Ethan. And yeah, so welcome everyone. I want to do this much like a walking tour. This is a mental model that I like to use for these sorts of trainings. We are a group, we are walking together, and we're going to get to know the language by walking around, by exploring the language. And so that's where I want everyone to be working with me, walking along with me. You can think of this workshop kind of like a tour of the Cathedral of Learning. Walking tour rules apply. So what are some good rules from a walking tour? Walk together, right? We want to stay together. We want to have keep tabs on each other to actually do something together. Um, what makes a good walking tour? A good guide. I hope I can come through on that. Some of the best walking tours that I've been on have been good because people ask a lot of questions. When people ask questions, it's often something that I've wanted to know, or, often tour guides, they just run off and do their own thing. And when people ask them questions, they actually are like, oh yeah, let's go. And that's when you get the interesting stories out of people, in general. I'm that way too. I'm going to try to, give you interesting stories along the way, but if you ask questions, I'm happy to explore things. The other thing about a walking tour is that the tour guide walks alongside you, right? Like, where I'm not coming from a different place. I'm going to start with a blank slate, just like you all are going to start. And so I went I'm going to do this live, and we'll explore this together. So we'll investigate lots of rooms on the first and second floor. I don't know if any of you have been through the Cathedral of Learning or have explored it. If you haven't, you should go take a look. It's a fun building. And there's a lot of really cool classrooms on the second floor that you can peek into, that like come from different communities and nationalities and different places around the world. And so there's lots of really cool corners to see, and so just like that, if there's something interesting in the what I'm typing at the moment, just raise your hand, shout out, and we can explore that room a little bit more in depth if you're curious. So we'll investigate lots of stuff on the first and second floor, and then we'll grab an elevator and sneak up to the 40th floor. You can get up to the 36th floor on the Cathedral of Learning publicly. And you get a nice view of Pittsburgh. There's a boardroom on the 40th floor that it's a little tricky to get to. Or you need to be invited to in order to see. But we'll sneak up there and check out the view from the 40th floor at the end. So that's the mental model here. Let's dive in. Let's just start playing. Let's go to VS Code. So I'm going to jump over to VS Code here. And I have this set up. I was looking at this. So I have nothing going on here. I've opened an empty folder. If you don't have this set up yet, just raise your hand and Ethan or Letícia can come and sit beside you and help you out. and we'll get everyone up and running. So the first thing that I'm going to do is I'm going to create a file, and I'm just going to call this juliacon.jl. And because I have the Julia extension installed, you can see I got the Julia dots right there. And we have this growing, and I'm just going to type in here, print line, hello, JuliaCon, and I'm going to execute that. And the way that I executed that is by hitting Shift Enter. That pops up the terminal at the bottom, which comes with the Julia extension. So if you can't do this or haven't done this, let us know, and we'll help you get set up. In the meantime, I want to get a little sense of where you are all coming from. So how many folks here have written 10 lines of code in Python? Yeah, 100 lines of code in Python. How about other programming languages, like 100 lines of code in MATLAB? Yeah. Or C? Wow. Okay. Awesome. How about what else? R? Okay. The Rust? Few. What other languages have folks used? Yeah. Chapel. Interesting. Okay. Yeah. Zig. Cool. Wolfram Mathematica. Okay. Nice. That's helpful for me to know, just like in what analogies are going to be helpful to the room, and where you're all coming from. How about Julia? 10 lines of code of Julia? 100 lines of code of Julia? Some? Okay. Cool. Um, that's perfect. That's right where I want you all to be, and where we're going to start from. So I'm going to not spend too much time on the mechanics of programming languages themselves, but really try to talk with analogies from the other languages that you all are familiar with. So the first thing to note here, right? So let's make this a little bigger. Let's make this bigger. How about VS Code? How many folks have spent time in VS Code before? What other editors have folks used, like Sublime Text or MATLAB or NeoVim, Emacs? Yeah. Okay. So VS Code is nice. The biggest thing that it does for me is it just gives you both an editor and a REPL at the same time in the same window. Makes it really easy to bounce back and forth between those two. The REPL is, as Ethan talked about, extraordinarily powerful. It's a great place to work. The one thing that I've done to my VS Code here that as I've customized a little bit, I try not to set too many settings because it ends up, yeah, I want this to look more like what you're seeing on your screens. The one setting that I've set here is when I execute a line of code from the text editor. So I'm up in the text editor section here. And when I hit Shift Return, it executes that. And you can see that it executed with the check mark there. And it sent the entire string to the REPL itself. By default, when you do this, if we just delete that and say 1 plus 2 and you hit Shift Enter, by default, I think you'll just see the number 3 and you won't see the 1 plus 2 appear in the prompt. And I find it helpful to see that in the prompt for several reasons. One is it gives you a little bit of a history, so you can see in the history of your shell what's happened. And it also makes it accessible within the REPL mode itself. So now into REPL, I can press the up arrow and go back through my history, and you can see the 2 lines of code that I've done there. So to do that, if you want to make this look like mine, you can go to the settings page, and the way to do that, I get there with the command shortcut, but you can get there just by going to settings here. There it is. So under code settings, under extensions, there's the, oh, whoops, that's not what I wanted. Settings, I want the extension settings. settings here. So hit this again. So if I search for Julia, there's going to be a bunch of Julia settings that you don't need to edit and change. But the one that I did change here is, where is it here? The code in REPL. So by checking this tick box, it will print the executed code in the REPL when I do that Shift Enter command, and it'll append it to the history. So that's just a little bit here that I've done in my customization. I don't want to spend too much time there, but it's helpful to know. So the first thing to do here that I want you all to start walking with me is play with Julia like a calculator. What are some good calculations that we can do with Julia? And don't think programming language, just think computer, right? Like let's run some code. Let's do some math. What are good yeah, start typing away. See what you can do. Use Julia as a calculator. What are some good functions that we can play with? So 1 plus 2 is very simple. What else could we do? Square root. How would we do that? Maybe square root. Nope, that's not it. SQRT. And as I type, you can see that there's documentation that pops up. Actually tells me a little bit about it. So I can say square root of 2, Shift Enter, and when I hit Shift Enter, it puts it down at the REPL, but it also gives me the answer in line there. So you can do square roots. What if I tried to do something like a -2? That's going to give me an error. It says domain error. And in fact, if I scroll up here, you can see square root was called with a negative real argument. So it gives me a hint on how I might do a square root of a negative number. What are other interesting things that we could play with here? Yeah, trig, great. Sine of 3 pi, say. That gives me something. 3 pi is a little funny. Maybe just do sine of pi. That gives me 0. We could do cosine of pi. -1. You can do, uh, 0.5 pi, things like that. And you can start seeing a little bit about the language, right? So we have a pi here, right? You can look, what is this pi? Well, it's the number 3.14. There's some magic that Julia does there to try to make it arbitrary precision. But that's interesting. Other thing that you'll note here is when I multiplied it, I didn't put a star here. I could do that like that, and that'll give me the same answer. So you can implicitly multiply. The other thing that I'm doing just without thinking about it is I'm calling these functions, right? So when I called square root, I did sqrt with a function brackets. This should be very familiar to all of you coming from Python, MATLAB. All the standard imperative languages use function call syntax very similar to this. One fun thing that you can do in Julia, though, is there's another way of spelling square root. You can use a symbol for it. And so if you've ever used LaTeX typesetting, you can get access to a lot more letters and characters than the standard ones that appear on your keyboard by typing \tab completions. This isn't actually a part of the Julia language itself. It's a part of tab completion. It's a part of how the language inputs text. So the \/ here isn't actually an operator or a function call. It's just a way of keying into tab completion. So by hitting tab now, I get a square root operator, and I can do something like that. And that gives me the exact same answer as if I were to have written it by myself. What are other interesting things that we can do? How about exponentiation, 10 to the power of 10? That gives me something that I would expect and looks good. What about 10 to the 18? That seems reasonable. 10 to the 19. That might be a surprise for folks coming here. It's one of the very first stumbling blocks that a lot of people come to. If you exponentiate an integer or get a very large integer, you can get answers that you don't expect. And what's happening here is, well, these are 64-bit integers. They have a limited range, and if you exceed that range, they're just going to roll over. There's some good reasons for that. A lot of it's because of hardware, and you want things to be fast in a common range of integers that you end up using. And in order to do that, this is one of the behaviors that falls out. Can also, there's some other reasons for it, but just know that that's a thing. In order to do this correctly, there are two ways that we can fix this. One would be to use floating point numbers here instead. And that prints out kind of like what I did, except it's in scientific notation now, 1 times 10 to the 19th. The other way to do it is with another operator called big, or a function called big. So big of 10 to the 19, that will actually tell me that, hey, we can use arbitrary precision integers here. This is how Python would work by default, where you can do something very large now and get lots of numbers, or something more interesting than a power of 10, right? If you take 3 to the power of 200, you get a much more interesting answer. This is now arbitrary precision, so it's a little slower, but you can go as large as you would like it to go. What about comparisons, right? So that's a common thing to want to do. 2 is less than 3. That's a true statement. 2 is greater than 3. That's a false statement. One fun thing with Julia is you can chain comparisons. 2 is less than 3 is less than 4. It's very Pythonic, for those of you coming from that. Not like C. This is a chained comparison. What about equality, right? So you can ask, is equal to, is 2 equal signs like that? And those are different. But, we can do this with 10 to the 10 or 10.0 to the 10, and those are going to be equal. So it's helpful just to kind of get a sense of language, just playing around like this. What about if I were to do equality with a single equals? What's this going to do? Yes, it gives me an error. It says I can't assign to 2. And equals here is not really a mathematicals equals, it's an assignment operator. It does something wildly different than the equals of mathematics. It is giving me a name that I can start working with. And so this is how we can start abstracting away. Everything in Julia can be named. You can assign names to pretty much anything in the language. And that's exactly what the single equals does here. And now I have an x that I can use at the REPL, and I can do subsequent computations with, right? So I can do x squared. I can do x squared plus x. I can add another number here, y equals 2.5. And I can do times y plus y squared, get a nice like polynomial equation here. So there I forgot to hit shift enter on line 2. So I'll shift enter there. And, this is how we can start working with it. So these are names. This is a little bit of a departure for those of you who may be familiar with some of the more traditional compiled languages where assignments have slots or locations. These are just names. That's all they are. It's just a way of us talking to the computer. The other thing that we can do here is we can introduce our own functions, right? So we talked about, being able to call sine of some number. We talked about being able to call a square root of some number. What are sine and square root here? Well, we can look at them, right? They are themselves functions, and we can define our own functions. And a common way of doing that is, or a common shorthand name to use to define a function is the f. So let's just say f of x, y is going to be this polynomial equation here. And so I can define that. So here, this equals sign is doing something yet different again. It's not only saying we're going to introduce a name f, but it's going to be a function that takes 2 arguments with those names, and it's going to do something when it's called. So now I can, my REPL or in my text editor, can start typing and say, what is this expression evaluated at different points. Um, and so this is how you start building out higher, more complex things than just using it as a calculator. Any questions on anything that I just went through? Real basics of language syntax. I didn't talk too much about the syntax itself, but just did it, and hopefully it made sense to you. If it didn't, now's the time to be, hey, yeah. It's part of the reason. So I defined this function here, and one of the things that happens is I've not compiled it yet, right? When you define a function, you've not really compiled it yet. Julia will compile it the very first time you call it. So that's part of the magic, but the big magic is how it gets compiled. And so what ends up happening, I've defined this function. I've not talked about types yet. That's very intentional. But I've been using different types throughout this. I've used integers, I've used floating point numbers. And when I called this f of 1, 2, I got a 7 back. If I call it with floating point numbers with a period in them, these are different things in Julia if you put a period in it, and it prints out differently. You can kind of see that. It actually computed it differently. And so I've now compiled f two different ways because I've called it two different ways. I've compiled an integer arithmetic method that knows how to use integer arithmetic on my computer very efficiently. I've also compiled a floating point method that knows how to use floating point methods very efficiently. This is called specialization. And if any of you have ever used C++, it's very much like how C++ will use templates, where at compile time with C++, it will automatically compile all of the possible ways in which you might call this particular template. Julia, we don't have a compile time, at least not the way that I'm showing it here. It's happening all interleaved. As I call it, it gets compiled. So let's call this slightly differently. Let's call f of, let's do a different, let's introduce another type here. Let's do instead of, do a complex number. Sure. So let's do 1 plus 2 times the imaginary constant. That's square root of -1. In Julia, it's just the name I am. 3 plus 4 times I am. And let's add a little special macro here called time. And, shucks, it didn't even bother compiling it. It's too simple. But this is going to give me yet a different specialization on this, that's going to, and I was hoping it would show me that some of the time was spent in compile time, but this is wildly simple. But you can get a sense of what's happening here. Do I want to do that? You can actually dig into Julia and see that now I have 3 specializations with 3 different code. And I guess the biggest thing that I'll do, just to kind of peel back a little bit here, let's look at the native assembly that this did. Let's do debug info equals none. This is me doing a little bit of extra magic here, but code native is a way of asking the Julia compiler, what did you do? I'm going to hide the line numbers and stuff. I know that flag. You don't need to use that flag, but it's going to tell me exactly what this did. And it compiled down into just a multiplication, an addition, and a multiplication and an addition together. So it did all 3, just 3 instructions to do that, and I didn't need to do the assembly. It's just there, and every time I call it with that, it's going to do that. And you can contrast that with a floating point operation. It's going to use floating point registers. So now these are fmuls and fadds, and it's slightly different. And so that's more to the key of like how it's fast. So we're standing atop a really great compiler infrastructure called LLVM that knows how to do this. It's what Google uses, it's what Facebook uses, it's what Apple uses, and so we can use that and talk to that in a very efficient way, and give you access to it just by writing something very simple. So good question. Yeah, go ahead. There is. So every time you run a new function with new types, it's going to compile something new. That gets cached, and so the trade-off that we make is that Julia ends up using a lot of memory because every time you call a function, it's going to compile it. That's not stuff that gets garbage collected. It's not stuff that gets thrown away once you've compiled it. It hangs out for you for as long as you're running Julia. There are ways of hooking into the compiler and asking it to delete methods and things, but I think they actually stick around because you might have called it and you might have code that's running that could have called it. And so that cache is there. And one last thing about this point, is, people talk about the Julia JIT, and it is true. It's a just-in-time compiled language. We are just-in-time compiling this, but it's very different than the way that like a JavaScript JIT works or other high-level language JITs often work, where what they end up doing is they trace the execution of what you're doing and they identify, oh, hey, this is a hot loop. Let's swap out the interpreted code for a compiled code. What Julia is doing is a much more akin to an ahead of time compiler, where ahead of calling any function, we compile it. It's just that we don't know when we're going to call a function, and so we carry around our compiler with us all the time, and we might compile it when we call it at some point down the road. But it is, yeah, it's just hanging out there. So I often like talking about Julia not as a JIT compiled language, but as a just barely ahead of time compiled language. You just barely, at the moment you need it, we'll compile it for you, and we don't know what types we'll end up compiling this function for. So you can do all sorts of things with it that way, and it makes it a lot more tractable than C++'s templates, for example, because those you need to know ahead of time exactly what combinations of arguments you have. We're okay not knowing what arguments you'll end up using because we'll just compile it when we see it. Great. So let's do something a little bit more interesting now. Let's start talking about a little bit of control flow and a bit more of a complicated function. So one thing that you can do with a function is you can ask, how long does it take for it to blow up to infinity, right? So we can take a function like this. Let's simplify this a little bit. Let's call it f of x is x squared plus x. And so now when I do f of 2.5, you can see it gets bigger. I can call that again. It's going to get bigger again. It's going to get bigger again. So you can ask a question, how many times do I need to call this until it becomes infinite, until we've blown up, right? So that can be an interesting question. And that requires some control flow, right? I could manually go through here and just call it many times. I keep calling it. Now we're at 10 to the 15. You keep calling this and you get a bigger and bigger number. But how many times do you need to do this until we blow up? So let's write a function that'll do this. We could write it as a one-liner like I did here, right? We gave ourselves a name of a function f and we use the assignment operator. I could also have written that exactly the same way, like this, by saying function f of x, return x squared plus x, and like that. These two statements, what I have on line 4 here and lines 6 through 8, they're exactly identical. The language does not care which one that you use, but this one is nice because it gives you a little bit more space to work with, right? Julia, we end up using a lot of one-liners, but it can be useful to do something more complicated than that. So let's create a function called blowup count, and we're going to ask how many times do I need to call a function or execute some algebra until it blows up, until it hits infinity. So how would I write this? Well, what's some good control flow that I might use here? How would you do this? While loop. Yes, exactly. So how would you write a while loop in Julia? You just say while, and if I hit enter, it's going to tab in, and we have an end statement here. And so I can say while. What do I want to do? I want to make x bigger until it blows up. I'm not sure what I'll put in the expression here for the test of the while loop, but what I want to do is I want to update or give x a new name, or reuse the name x, and let's say x equals x squared plus x. So what do I want to do? Well, while x is infinite, or x is less than some number, or we could use all sorts of things. There's a function in Julia called isinf x, but I want the opposite of that. And so how do we do the opposite? We do a not with an exclamation mark like that. So that's while x is not infinite, we're going to reuse the name x and do some computation and do that. And we're going to return, what are we going to return? Well, we want to count, right? So maybe a while loop, this would work, right? But what we want to do is we want to return how many times we needed to do this. So we could say count equals to 0, count plus equals count plus 1, and we're going to return the count, right? So that gives me a function that we can run. Yep. And I'll execute that. Sorry, it wants to jump around. I'm trying to keep it on the screen here. So we have a function, blow up count, and we can just ask how many times does it take for squaring and adding to explode when we give the number 2.5. So that works. There's another way we could have written this, though, in a way that's a little bit safer, because what might happen if I give this a small number, right? If I give this a number, well, if I give it 0, what will happen? It'll just keep looping forever, right? Because 0 plus 0 is 0, and it'll never hit infinite, and so we're going to have a problem there. So let's restructure this a little bit. Let's, instead of using a while loop and manually incrementing a count, that's very much like a, what is that? For loop. Yes, exactly. So let's use a for loop here. So this is the syntax for a while loop. It's very straightforward, but more common than a while loop in the language that you'll see in Julia and in most languages is a for loop. And so we can say for count. And what do we do here? So count is what we have. We want to increment count from some value to another value. We can say for count in and some set of values that we can choose from. And one way of doing that is by using this colon syntax. It's like range in Python. We can say 1 to 100. And now we don't need to update count there. We don't need to update count here. But what we do need to do is we need to do something a little different here, and that is what happens if we, like, where's our break point? Well, how do we know that we broke out? And the answer is, well, we need to add an if statement. We need to say, well, if is inf. Now we can use the little bit easier way of writing this. So if x is infinite, then we will return the count of times that we needed to do that, and hit end. So that gives me my function. And if we didn't hit the x, if we didn't hit this, maybe what we want to do is return 100 plus 1, right? So we did 100 iterations. We don't know, maybe we'll just use that as our sentinel to say we didn't make it to the end there, and that will give us this. So now I can safely say blow up count of 0, and that'll just give me 101. I can still do blow up count of 2.5, and that still gives me 10. So this is a nice way of writing this, of coming through here. What if I started looking at at slightly different numbers, right? So what if I did, instead of 2.5, I did 2.0? That also takes 10 iterations to do this. Oh, one thing that I wanted to point out here before we did that. Sorry, I'm jumping ahead. I wanted to talk a little bit about this colon syntax. What is this, and how does it work? Well, I can just, with anything in Julia, you can kind of copy little snippets out, and they should work exactly the same as in different places in the syntax. So I can just copy this little bit out and paste it at the REPL, and I get back exactly the same thing that I wrote in, right? Like that doesn't seem very helpful. If I don't know what 1:100 is, Julia spitting back out 1:100 isn't going to be very helpful. I can ask for help on this, since this is what Ethan had talked about. You can put a question mark at the very first character of your prompt, and it changes to help. And if I ask for help there, it tries to get some information about what I did. And what it saw here is the colon. And it saw that I was using the colon function call. And what is colon? That's a good question. So you can, again, put a colon at the REPL prompt, and it just prints out something that's maybe even a little bit more confusing. It says it's a colon, but it's a function. It's a function that you can call, and we can uh, kind of play around with what it gives back. So R is this 1 to 100, and you can look at it. You can ask, well, what's its size of this? Is 100 elements. You can ask all sorts of different functions that Julia has. You can ask what the length of this R is. There are 100 elements in it. You can ask what the first element is. That's going to be 1. You can ask the last element. That's going to be 100. So this is an inclusive range from 1 to 100, and it's the very nice syntax. It's the same as if you were to say a range from 1 to 100 like this. You could also do it as a range operator here. This is going to work subtly different than a Python range function because we are one indexed. So R is like an array here, and I can get the first value out of it, and it gives me a 1. I can get the 100th value out of it, and it gives me a 100. And that looks somewhat not helpful. It becomes a little bit more interesting if I did a more interesting range, like 3 to 22. R of 3 then is the third element of that. So we have 3, 4, 5. That's our third element. So Julia is one indexed. If I tried to index this with a 0, it's going to give me a bounds error saying, hey, we tried to access this 20 element range at index 0. And that's not an allowed index for this one. You can use offset arrays if you really have situations where you want to use a 0-based index, but in many cases, 1-based works well for the kinds of things that you do in Julia. There's not really a right answer. There's a lot of hot takes on the internet about which one is correct, but it really depends on what you're measuring. If you're talking about distances, then we use 0-based indexing in our real life. You start a measuring tape at 0. If you're looking at counts of things, then we want to use 1-based indexing. And generally in Julia, you end up talking about counts more than how far away you are from the beginning of an array. Okay, so that's a lot there about ranges. What ends up happening in the for loop, though, is we end up iterating over this. So there's a special thing called iteration, and it's just a way of grabbing a sequence out of some Julia object, and that could be a range like this, and that's often how you'll see for loops written. Yes.
Will you you're creating that I guess one question is what's the name of that type? It is a list, an array, anything else? And is it also allocated or is it
So the type here is a unit range, and there's a new syntax here that we've not seen yet with curly braces. You can start getting a sense of what that does. If let's see, oh, it's not gonna actually. Let's do it like int 8, 1, 2, and 8. There we go. So you can start getting a sense of what the that's not the one. So 1 to 100. And if I change the types, you can get a sense of what these curly braces might be doing. Um, the so it's a range operator, and what that is a type it's like a vector. So I can actually say um, 1 to 100. There's a special operator in Julia called ISA, and I can say, is that an abstract vector? And it'll say it is. And so there's this abstract supertype, for those of you coming from other languages that'll be familiar, where you can opt into vector-like behaviors. What actually is this? I can dig into it a little bit. There's another function called dump that will tell me exactly what data is stored here, and it's just the start and stop, and so everything else is computed on the fly. But it behaves exactly as though I were to have written an array. We'll talk about arrays in a moment, but you could have also written this as a list like this, like go on and on, right? That also gives me, no, it's actually going to tell me it's a vector. This is similarly an abstract vector, if I can spell. So these things behave in some senses very similar. This one is actually storing all of these numbers because it doesn't know that they're sequentially increasing. Yeah.
Two questions. First question: am I using Visual Studio like this, and I was completely enabled the settings in my variable setting?
Yeah.
And I want to start over.
Yeah.
I quit Visual Studio and nope.
The best way to start getting a sense of getting better at Visual Studio Code is to start using the command palette. And there's a menu item here somewhere. Yeah, on my Mac, it's under the View command. There's a command palette there. I know that's very tiny on the monitor, but I just always find it with the keyboard shortcut, which is Command Shift P on a Mac or Control Shift P on a Windows machine, Linux machine. And when you do that, it pops up kind of a command line interface to your REPL. And here you can type Julia restart REPL. And that will clear your state, get you back to beginning. This is also just a really nice way of getting a sense of VS Code itself. So there's a bunch of Julia specific commands, right? You can kind of scroll through here and get a sense of what else we could do, right? Like what I've been doing this entire time is I've been executing a line of code in the REPL, right? Like one of these, I think maybe this one. Yeah, it's Shift Enter. That's what I've been doing. So not only does it give you the text of what it is, it also tells you what the keyboard command is to run all of these things. It's really helpful just to explore and get a sense of, of what all is available. Not just for Julia though, too. There's all sorts of like indenting or standard text editor stuff too. Very helpful. Yes. Typing hints. Yes. So the question is, how do you write typing hints in Julia? We'll get to that. I'm very intentionally, we've seen that there are different types, but I've not written any types yet. I won't miss that. I promise. Go ahead.
Obviously, go use the function last.
Yes.
How do you find that?
That's a great question. So I scrolled through and I did a whole slew of function names that I know, and it's just kind of magic, right? So we have length, first, last, range. What are all these functions, and how do you know where they are? Um, these are all things built into the Julia standard library, and they're all part of the base Julia library. One way that you can start exploring them is there's yet another name that you can use called names. You can ask, what are the names available to me? And see, I don't think we don't support calling it with no arguments. You have to pass a module, which a module is what encapsulates code in Julia. The default module is main. So here you can see that I have 9 things that I've defined in my my workspace so far. These are the, we have the F, we have the R, that range that we were talking about. We have X and we have Y, we have that blow up count. Um, we also have these three things that I've not talked about, right? So I've just said that there's a main module, and so that's what main is here. That's how I have access to that. But there are these other modules, base and core. These are the built-in kind of the batteries that Julia comes with. So I can similarly ask for what are the names in base, and there are 1,000 different things that I can call. That it's such a long list, it's elided here. So that's one way that you can do that. You can look at it this way. It gives me back a list of all of them. It hides some. Another thing you can do just to kind of explore the language is hit tab twice, and that will give you all the things that could possibly get tab completed. So somewhere in here is first, last, square root, sine, all of these things that we've been talking about. Yeah, here's last. And so sometimes it's just helpful to start typing, right? So I know square root, I'm going to start with SQ. And if I just hit tab, that's the only thing that's available to me that starts with SQ. That's a lucky one. With last, if I start typing L, there's a lot more things that could be available there. But this gives you a sense of how you might start exploring the language. There's of course also documentation and help. If I let's see, what if I did? There's a way to search the help command, and I'm trying to think if there's a helpful search like final maybe. Um, yeah. So if I didn't know the name last and I wanted to get the final element or something like that, right? Like, and I just ask for help on it, it'll try to search for the names themselves. That can get you somewhat. Sometimes that's enough. Sometimes it's not. You can also ask for. There's another name that's available that can be helpful is apropos, final like this, and it'll list all of the commands that have that in their documentation. But I don't know if last actually appears there. so so it can be hit or miss. The last answer is of course there's the documentation online, docs.julialang.org, or a large language model. They're great ways of finding things like that. Good questions. I appreciate the time here. Okay, great. So let's go back to our blow up count here. And so we've talked about syntax. We've talked about the way in which you do this. We've talked a little bit about different types, right? The ways that we can use integers, complex numbers, floating point numbers, and arrays, ranges, and such. Um, what Yeah, let's just take one last step back and talk about names one last time. So in this function, I have this x here, right? And I use blow up count of x, and I'm updating x inside this function, and I'm asking if it becomes infinity. Then I return something. So what happens if I say x equals 2.5 and I do blow up count of 2.5? What's x going to be now? Says, so if I reevaluate x, what's it going to be? Any guesses? 2.5. Yeah, exactly. So it didn't change, right? So why did this not change? Why did this name stay the same? But inside here, at some point, it would have changed, right? And so this gets to the idea of a scope. And so it doesn't matter what names you use for things. When you pass things, you're not passing their name or their variable, you're actually passing the thing itself. And so when I ran this, there's nothing special about the name X here. I could have just as easily used the name Y and done 2.5 and did blow up count of Y instead, right? Like that's going to give me the same, it's not going to change Y, because and it's definitely not going to change x. Those things are distinct, and that's because inside this function there's a scope, and it's like a room. Those of you coming from other languages familiar with scopes, the thing that Julia does a little bit differently, particularly from Python, is we like creating scopes. You'll often find that Julia creates a new room for you, or a new scope that where Python wouldn't have. And so it's just a different context section where X is going to be different on the inside versus the outside. And the most important part about this is that these things that I'm assigning, they're names. They're not boxes. They're not labels. They're not tangible things. They're just names. And so it's very much akin to how I have multiple names. You could name me multiple things and it's fine. Different people call me different things. If you go into my house, you might hear that my name is Dad. If you go into someone else's house, Dad's going to mean someone different, right? Like it just we're very well attuned to this, but somehow when it comes to programming, this can become one of the most complicated and mind warping things that these are just names. I think that helps folks' mental models in some way, that you don't want to think about them. Definitely don't think about them like pointers if you're familiar with C++ or C, because they might not even exist. We don't have locations in memory where these things live. They are just names that are available to us and to communicate to the compiler. I have a little bit on here. Let's see here. Where is it? Yeah. So, yeah, this is a lot of what I talked about in that little segment. They are just names, and they are just conventions. The thing that I want to talk about though is you'll see lots of one-letter conventions in Julia. We already used X's and Y's, just kind of random math stand-ins. I's and J's are often loop variables, like they're often integers. But they don't have to be, right? You could name them whatever they wanted to. You'll often see capital letters, capital single letters for matrices. F's and G's are often functions. Capital T for a type stand-in often. There's nothing special about the names that we use. You can always change them. Okay, that's good enough for now. Why not? Why do I make this remark? So I don't like variable because variable implies that there's a state to it. That like for me, for my scientist brain, I think of variable as something that I can change. When I have a variable, you can decide to use that name in a different way, but it's not really changing anything about the object itself. It might not actually make an effect in the program itself. Assignment statements aren't changing anything fundamental. They're just reassigning. They're just changing what you're going to use a name for. So concretely, right? Like you can say x equals 2, y equals 3, and then x equals y. And now if I decide to use a different, depending upon the mental model that you have, you may or may not think that these two variables are linked, right? If and particularly if you're talking about a C, if you have a pointer or something like that, you can think about this as being a box and a space. These two things aren't linked. When I do x equals y here, it's not saying that x and y are going to be the same. It's saying I have a name x that I'm going to use for whatever I'm calling y at this particular moment. And so if y happens to change down the road, y equals 4, x is still what it was back here, right? There's nothing that is that's stateful about. The only part that's stateful is that they are the names that I'm choosing to use right now.
Or just any sorry, X or Y, Z. But if you use something that's box, yeah.
Yeah. Exactly. So that's intentional. So what we're jumping a little bit ahead, but that's perfectly fine. So what if I were to have changed this to be x equals an one element array like this with the value 1, y is equal to x like this. And so now y and x are both this name. Now, if I decide to change, let me give myself more space here. So I have an array. I have two names. I have an x and a y. And if I decide to change x's name to something different, like this, then is y going to change? No, because it's just the name, right? It's just that there's nothing changing here. That's exactly the example that I did with the integers. The part that's tricky though is that this object might itself be changeable. So the names themselves are what we talk about, how we communicate. The objects, that's the important part. So the object in this case is the array itself. So let's start again. X equals an array of 1 and y equals x. And now I can change this object. And it's not really changing x, it's changing the thing that I'm calling x right now. So I can update the first value of this to be 2. Now I have a one element vector that whose value is 2. And y is a name for the same array, right? It's this array here. And so that also, I don't really like saying also. It is just two names for the same object. And so no matter whichever name I use for that object, it is going to reflect the same thing. It's again the same as if you told Matt to walk out the door or my daughter told dad go walk out the door. I'm the one that's making the change. I'm the object. I'm the thing that's important here. The name that you used to issue that command doesn't matter. Yeah, go ahead.
If Scobie is so complicated as such a map, what good are it? What good is it?
The best thing that scope does for us is it limits the concerns that you have to think about. So you don't have to think about anything beyond what you can see on your screen. And so it's often called lexical scope because it has to do with how you read things. And so going back to here, right, this function, I don't need to know anything about outside of these 10 lines of code, 9 lines of code. This describes an entire little ecosystem that is purely self-contained. There's nothing I need to know outside of it besides a few particular constants that it's using. So what is it using from outside of this ecosystem? So we're passing in a value x and we're updating x and then we're calling some names from here, right? So it's pulling out, well, the colon operator is inf, the square, the plus. These are all names that it's pulling from a global namespace, but it's all in a kind of self-contained thing. And so that's where scope becomes really powerful. I can change this to make it a little bit more complicated. So one thing that I might want to do is maybe I want to dig a little deeper, see more than 100 iterations. So for example, let's go back to blow up count and do something a little bit like, let's do 0.26 maybe. 0.25. Here we go. So if I have something small like this, right? I have a small value, it's going to saturate. If we hit the max iteration count. So I can go in here and I can say, well, let's update this. Let's do max iterations equal to 1,000. And let's use this name inside here. So now this is going to use a global variable. So I can execute this, execute that. And now I have the ability to say, okay, so let's do blow up count of that 0.1. And we've gone now beyond our 100 iterations from before, right? And so this is using a name from outside of our scope. And this can be a little bit complicated now. Like there's state outside of this, because this I could choose to assign a different thing to this. I could choose to say, well, if I change my max iterations to 10 and rerun this, now I'm going to get a different answer. Should. Oh, yes. Right. I need to change this. Thank you so much. So I had hard coded the 100 down there. I also want to update that. So there we go. So now we only get 11. Good. You scared me for a moment. So this is, where you start using a global from outside of your function. You can end up, it's a little harder to track your programs. It can become spaghetti very quickly like this. And it can be a little harder. And then it's also harder for Julia itself to optimize this. So because I can decide to change max iterations, I could change it to some other type. In this case, it doesn't make sense to use anything other than an integer, but I could, and Julia has to defensively compile its code to handle that case. Go ahead.
So you run the gambit, do lazy, and you're like taking figures, do you put it during the was always we should find
Yeah.
like 1,000, but don't put a period.
Well, so that's because it's a for loop for max iterations, right? Yeah. So if you have the while loop,
It's always the very nice one, presumably because that infinity you never pre-put in here.
correct. Yes, exactly. Right. So we could restrict this. So this is the way, right? We've not talked about types or like defining types yet, but let's look at isInf first, and this will give us a hint about how we can define this ourselves. So isInf is a function, and we've seen this printed out multiple times, but I've not talked about it yet. There are actually 5 methods that implement isInfinite. And what are those methods? You can ask. Well, it's dig in, and you can see it'll print out exactly how isInfinite is defined. There aren't many implementations here. We have 5 implementations, and let's see. Yeah, will it actually do this? So I can go to, so this is, to answer the question from before, how you specify types in Julia is with these 2 colons. So anytime you see a variable with 2 colons, it's doing a type annotation. It can mean several different things depending upon the context, but this is a type annotation here. And it gives us the ability to say, this method will only apply to big floating point numbers, or this method will only apply to either, double precision floats with 64 bits, single precision with 32, or float 16s, or anything else. So I think if I command click on this, will it open it up? Maybe it won't. Yeah, okay. So there's a little trick here. Whenever you see a command list printed out like this with numbers, you'll often see method lists like this. Whenever you see this, you can actually dive into them with a little shortcut at the REPL here by typing the method that I'm interested in, and then typing Control Q. It will open that method definition. And Julia is written in Julia itself almost entirely, modulo LLVM and a few of the compiler thingamabobs, but most of Julia is written in Julia itself. And so this is how isInfinite for all real numbers is programmed. Well, not very helpful. It's just two more function calls here, and this is very common to see. There's isNan and isFinite. Let's see, do I have oops, I don't want to start editing that. IsFinite. Yeah, we do have isFinite. So I can look at isFinite, So it's the inverse operation of is infinite is finite. It's not infinite. So is infinite is defined in terms of not being finite. So I can do exactly the same thing as I did with is inf. I can ask for those methods, and we have a lot more of these here. And here's one for all of our integers. And so again, that's the sixth one there. So I could type 6, Control Q. And here you can see that all integers are definitionally finite. Just by the way that the language works, these integers are going to be finite. You don't have they don't have the ability to express any concept of infinity.
I think the answer made both. Is it important?
So that's a good question. Is inf actually defined for integers? And the answer is they are, but it's not in a very obvious way. Um, the there's a hierarchy here of supertypes. And so we can ask, so what's the type of an integer is an int64? We can ask for its supertype. That's a signed number. You can ask for that supertype. That's an integer supertype. You can kind of walk your way up here. Supertype of that is a number. Yeah, I think there's a way to get the whole type tree, but is it? Oh yeah, sure enough. Oh, I need the type of, yeah. Thanks, Jorge. Yeah, so this gives much easier than manually walking through. This gives the whole hierarchy of inheritance that's happening here. So an integer is an abstract type that is signed, which is the abstract type integer, and real numbers are a part of that. All numbers are this. So we can do the inverse operation here. We can ask what are the other subtypes of real, for example. And so you can see integers are there, as well as all the abstract floats, as well as all the abstract irrationals. So this is how you can start thinking about the type tree. The number type tree is probably the most complicated one in all of Julia. There's a lot of different numeric types, and it gives you a good sense of what's happening here. So what happens when we call is inf of 2? Well, again, the methods here gives us a little hint here. You can see that, there's a real method here, which integers are reals. So that's one way you can think about it. The other way is, again, with this special macro. So I've done this several times now, but I'll describe it a little bit more carefully this time. There's this at symbol, which is a macro, which is kind of like a arbitrary keyword to the language itself. And I can ask which method is going to be called for is inf. And it is indeed that real method here. So good question. I appreciate it. It's helpful to start thinking about this. So then where we started down this road, right? Let's close this float.jl is actually in the implementation of Julia itself. Let's go back to our JuliaCon scratch work here. The real question was, so does blow up count actually make sense for things other than floating point numbers, right? So we could decide to do exactly the same syntax that we were seeing in that is inf methods trees by adding a type annotation here and say this is going to be a float, or maybe let's call it abstract float, right? So all abstract floats can now do this, and that's the only one. If I just run this though, what ends up happening is I add a method. So even though I'm using the function keyword here, really the appropriate thing that you can think of here is that this is adding a method. And now I actually just have two methods of blow up count. So I can still call blow up count with an integer because I had already defined it. And like we had talked about, these definitions don't go away unless you explicitly delete them, or tell the compiler to delete them, which is a very advanced thing. It's possible, but it's hard. Um, yeah, right. I could decide to say, yeah, maybe that's a easy way of fixing this for our interactive thing. Right, I could say blow up count of X is for everything else. Let's call the error function and say not defined. And so now I still have two methods. And if I do blow up count of a 2, then that's going to give me that error. And it's exactly as I wrote. Yeah.
Use your code data check. So,
Yeah.
what is it?
Yeah. Yes, correct. Yeah. So when we had done is inf on 2, right, that's false. And if we look at code native here, which is the question, sorry, I should do better about repeating that. Um, you can, yeah, that's a little, there's a lot of things going on here, but it's just a some move operation. Code native is a little hard to read, right? You need to understand assembly. This is the native language of my processor, and it's going to be different for different processors. The common architecture here is that LLVM compiler. So this code LLVM does something similar. It gets us an understanding of what it's going to return. And here it's just going to return a 0 or false, basically, right? It's saying that this is going to do nothing. And which is interesting, right? Because it's if when we looked at the method there, right? So we looked at methods of as env, and here it actually is defined to do something, but Julia is optimizing this, removing all these extra function calls. It this is what Julia does well, and it's part of the performance that Julia gets is that just goes away to nothing, and it just knows that it'll always be false. And so when you did this, or when we did this and we're able to pass an integer to our blow up count, then we ended up with yeah, with this being like just an infinite loop. It'll in fact know that this will never happen, and it won't even include this code. Yes.
Okay, so we have put that I specify around there.
Yeah.
Then now the way you had it set up, that will be you here to follow with an error.
Correct.
Yeah, what if you wanted it to seal this? No, sure, you could bring me if it was so they play for you.
Yeah, good question. So Ethan talked like about promotion, right? Like that's one way that a language that we use around computer science often is you want to promote types or promote to different types between things. And there would be several ways of doing this. One could be to explicitly say, and this is very common in Julia, we'll just call blow up counts again in the general thing and ask, there's a float function that will try to convert X to a floating point number. So we can define that instead of a error function. That's a really nice way of kind of explicitly saying, let's make this a make this a floating point type. And you can see that it has a definition here, and you can, when I hover over it, it popped up and it'll convert it. Great. So now let's run blow up count of an integer and oh, maybe. Oh, I didn't define it. Yeah, I didn't define it. So there I defined it, and now it is actually doing that. And so in Julia, promotion is a very explicit step. It's something that you explicitly opt into. But some of the functions that you call might do that for you, right? They might do that explicit promotion. And so an example there is when I add 2 plus 3.5, the way that this is implemented is it promotes these two values to a common type that it can use, and it gives me back a floating point number. And so that's most commonly where you'll see it. You'll also see it in cases where you are creating an array. So we've done this several times now. You can use these square brackets to create an array by just, putting numbers in a list. And if I do all integers here, it's going to give me a vector of integers. But if one of them happens to be a floating point number, it'll promote all of them to a common type because it's just wildly more efficient to have a common numeric type than to have a bunch of different types. And so we take the opinionated stance that we'll promote them for you into a common type, and hopefully that's okay for what you want to do. Yep. We are just about at our 10:30 break. I want to do one thing before we break because then we'll come back. Letícia will talk a little bit about packages and how you can start using more than what's built into the language, and then I'll come back and finish things up. We'll come back to this blow up count. But I want to change this just a little bit and make it get ourselves just a step closer to where I want to go with this. So what I'm going to do here, I'm going to go back to the way we had defined it initially. One thing that I want to do here, let's get rid of this. Let's get rid of our type annotation. We'll just have our one argument again. I want to remove this global because again, right, this 1000 is misleading because I'd actually redefined it in my REPL in a different way, and max iterations is no longer 1000. Let's move it into the appropriate scope. So I'm going to cut that and paste it as an optional argument here. And actually, I'm going to change this. I'm going to make it a keyword argument. So this is a little bit of Julia syntax that's a little fiddly. When I use a semicolon here, it defines a function that can take a keyword argument. And a keyword argument is exactly like an argument. It's just a name that has a value, but it's passed by the name itself or by the keyword. And so here I have a blow up count X and max iterations like that. And now I can dynamically change that when I call it. So if I call 0.1 like this, let's do a small number, right? Because it's I want it to take a long time to blow up. Right, so here we've maxed out our blow up count. We're at 1000. I can now decide to change this. So this max iterations value, I just say max iterations, and it's actually tab completable. Julia knows that that's a keyword, so I just started typing even M, and it'll tab complete it for me. And now I can make this 10,000 iterations or however many that I want to do, and you can see how long it takes to blow up there. So that is a little bit of Julia syntax. These are kind of like I like to use keyword arguments as the how something is done. So the data themselves, or the operation that you do, those are the positional arguments. Keyword arguments tend in Julia to be about the how. So that the positional arguments are the what's. These are comma separated things, and the ones that you pass explicitly by name, those tend to be more about like the hows of how many iterations, or which particular algorithm you want to use, or those kinds of meta questions about what you're programming. Whereas the data themselves, the thing that you're squaring or the thing that you're actually doing some processing on, tend to be positional arguments. For those of you coming from Python, watch out here, because in Python, you can use these two things interchangeably. You can, decide to put a positional argument as a keyword argument, or as keyword argument as a positional argument, and you can do either or. In Julia, they are very distinct things, so I can't, just call blow up count with with two arguments without explicitly naming max iterations here. And so that's a fundamental limitation, but it also kind of helps structure your program. Okay, let's do one more thing and then we'll take our break. So we had talked about one way to solve our problem of the isInf not doing anything meaningful for integers, by restricting this to abstract floats. We still have a bit of a problem though, because our blow up counts here, if we look at, how many times does it take to blow up with 0.01, it's 114 iterations. But what if I used a slightly different flavor of 1/100th, right? And I did this as a floating 32-bit floating point number. So I could do that explicitly by calling the function float32 that'll convert that to a floating 32 point. And you can see I get a different answer, which is interesting. Why would that be a different answer? Yeah, exactly. The size of the precision is lower, and I could even lower my precision further with a 16-bit, and this will be, even different, right? The number of times that I can square this before it hits infinite. The infinities are different. The maximum values are different for these different types. So maybe instead of asking, is it infinite, it might be a little bit more interesting to ask, is it going to become infinite at some point? And I can know that if if the absolute value of x gets to be bigger than some number, it'll eventually blow up, right? And I know the algorithm that I'm using here, and I can define this. And now those three things should give me the same answer, maybe. I thought. Maybe, did I actually evaluate that correctly?
Use definition.
It should be. Oh, maybe it is. It can get a little messy here. Yeah, okay. It's because I had added the keyword argument. And I had already defined what it means to call it without the keyword argument. Thank you, Jorge. So yeah, that's just a matter of having a little bit of state left over from our interactive explorations. But now, because this is just checking to see if it gets beyond a number that I know will blow up at some point, I have this here. So that gets us set up to where I'll want to go after Leticia's section on looking at packages. Let's take our break. Let's plan on coming back here at, what do we want to say, like quarter till?
Yeah, you can have it.
Yeah.
I'll come up for it.
Great. And yeah, don't hesitate to grab any one of us during the break here, and we can explore things.
Okay, so coming back from our break, now we'll talk a little bit about the package manager in Julia and how you can manage dependencies and different packages. So I will briefly introduce what this is about. So Julia's package manager is called BKG, and it is designed around building environments. So if you have used Python, it's something similar to PyM, for example, but it allows you to build environments on your system and your computer and move it around, and you are able to just continue working on that environment and continue working on your project uh, from where you left off, because you can immediately use and reinstate this environment in a new computer, new machine, uh, or in a different system even. So this consists of independent sets of packages that can be local to an individual project or shared and selected by name. And I will show you an example of how to build an environment. But the idea is that you'll have, at the same time, you'll have versioning control of all the dependencies that are installed in your environment. And you can ensure by doing that the reproducibility of the project across different systems and computers. So this resolves a lot of problems that people have with dependencies in general. And uh, let's get started with this. So the first thing, you can access the package manager through your REPL. So there is a module on your REPL, a mode in your REPL that you can use to just use the PKG. So if you type in your REPL square bracket, you are going to access the package manager. And to create an environment, you can use the command activate, and this will immediately create a new project. Once you do that, you create two files, one called manifest and the other one called project. They are written in this Tomta obvious minimal language, so it's a TOML file. And let's just open these files and see what's in there. So this is the example of the environment that I just created. Again, you go to your REPL to go to the package manager mode, square bracket. So here, square bracket, I'm in PKG. If I look at the manifest.toml, I will have the version, the Julia version, the manifest format, the project identifier, project hash, and then all the dependencies, versions, identifiers, everything will be defined in this file, which will guarantee that you can just rebuild and reinstate this environment when you want to continue working on this project. And then you have the project TOML, which is much more simplified and tells you the dependencies, the packages that you are using. And if you go to Julia's documentation, you can see here more things about the project and manifest files. So for the project.toml file, it will tell you what are the fields that you can add to that file. So you can add authors, name if you're creating a package, version of your package. You can add more dependencies, sources, compatibility. So you want to define, for example, oh, this package or this environment is compatible with this version of this package or from this version on. And manifest.toml, which is usually established automatically, will have more details on each one of the dependencies. So here, the documentation describes all the entries in the manifest file. So if you want to read more and know more about the format of this file, how you can edit it in the proper way, usually we edit the project.toml. If you are creating a new package, you add authors, you add sources, compatibility, you can edit this file usually. Okay. So going back to VS Code here, in this environment, I already added some packages, but I will show you how to do that. So using the activate, you can create this environment. Now let's add some packages. Let's add, there is a package in Julia called statistics, which has functions for statistical analysis. So you are in the package manager mode. You can just type add statistics, and it's going to find the newest version, and it's going to precompile, and it's going to show up in your project.toml file and also in your manifest. So this is what happens whenever you want to add new dependencies and new packages in your environment. And then when you type activate again, you are going to activate this environment with all the dependencies already activated. So these are packages that are local to this environment. You can also add packages to your like general or base environment if you just, instead of activating an environment, if you just add a package. So for example, I'll open here. Okay, this is my terminal, but just real quick. So I'm in the package manager mode. I can just add a package. I can add statistics. If I do that, I'm adding to my base environment, which is my Julia version 1.11 environment. So whenever I restart Julia, I can just use this package. And that's what we are going to talk about now. So we added the dependencies to our environment. How do we use them? So in Julia, you can use the command called using. So you can do using statistics, and this means the package is imported and you can use all the functions available there. And you need to do that every time you are using your dependencies. And there is a nice trick. If you do using and for a package that is not in your environment, see what's going to happen. Oh, actually it's in my general environment, so I need to think of a package that I don't have. Yes, I can use that. Okay. Yes, so I don't have the package in my environment, so it's going to pop up package example not found, but a package named example is available from a registry. Install package, and then you can just do it. So you don't even need to go to the package manager mode. You can just import the package or use the package, and this is going to ask if you want to install it. And then, as you can see, it's in my project.toml file. Okay, so that's basically how you manage this part. Let me go back to the presentation. You can also, there are more things that you can do in the package manager mode. Let me go back to my VS Code. So you can remove packages. So you just use remove, and then you can, let's remove example. There you go. And then your project.toml and your manifest files are updated, and the dependency that you don't need anymore, it's removed. You can also do other things. For example, update one of the packages that you have. So you type up and it updates the package. And there are also more options here. If you look at the documentation, managing packages, working with the environment. Yes. So if you want to know, for example, if you have the most up-to-date version of a package, you can also check the status. So you can use command st. So you can see, for example, here, st. And then it shows you version of each one of the packages that you have in your environment. You also have options. For example, there is something called garbage collector, which basically, if you are not using some of the dependencies in your environment for a very long time, if you run garbage collector, it can clean up your environment and remove some of the dependencies that you are not using. And to run garbage collector, you just do GC. So here, JC. And it's going to delete packages that you are not using, and all its kind of parent files as well. You can also use the package manager with its API, which is very cool. So if I go here, I can just do using pkg, and then I can do pkg activate, for example. And then I can use all the functions from the pkg mode through its API, which is very cool. So if you're scripting, this is very useful. And let me go back here. So these are the main things that you can do with a package manager. There is a whole lot more that you can do, and you can always look at the documentations and the different pages and everything. You can also use the PKG, and you should use the PKG to help you develop new packages. And I showed you that activate is the way to go when you are creating an environment. When you are creating a package, you use the command generate, and then it's going to generate a package with its structure, and then you build your code and you build your package around that. So we can do that as well. So let me go here, and then let me generate intro Julia. Yep. So when I generate a package, I generated this package inside this environment. Not the best idea, but just to give you an example of how to do it and which files it generates. If you use generate, it's going to give you a file which allows you to create a module. I'm not going to go very deep into how to build the module and how to build the package, because this would be a workshop in itself. But the idea is that by creating this module, you provide the name of your package. You can import files, you can import packages, you add all your dependency tree here, you define all the functions that you are exporting. And this is basically where you define your whole package as a module. And then you also have a project.toml file and a manifest.toml file. And here you can see that when I generated this package, it already added me as an author. It added its own version and its own identifier. So this is what happens when you use generate. And then if you go a little bit deeper, you can also register this package later. So your package will be available through the package manager mode by just doing what I did with the other packages. So if you do using and then intro Julia, if you've registered that package, you'll be able to install and distribute it in that way as well. And I think these were the main things I wanted to highlight about the PKG. Yes.
How do you do this if you're making a local package? So you make your module, you can precompile it wherever you have your local package, and I want to use that package in another project. So I made a local package, it's not ready.
I see. Yeah, that's actually doable and relatively easy. When you do add, you can go, for example, I'll go to a package that I have locally, but it's not registered yet. So I'll show you an example. So add, if I search my paths here, I can just go to projects, and then I have this package here, basissets.jl. This is one package that I have. And if I do this, add, it's just going to add the package. This package is not registered, but is local to my machine. So you can just use the same command. You just provide the path. If you have a module file, if you have your source code, everything defined properly, if you just do this, it's fine. And I can also remove it. So wait. There you go.
So you remove by name and then you add by.
Exactly.
Is so what happens is if a pack gets deleted and my package is on my machine and I need to correct my new project. So I have to know the name of the package to remove it, or wait, she just had us automatically resolve all of this package about the year.
Wait. So you're in a situation where the package you have locally, you want to add to your environment, but not all the dependencies of that package are available here?
Several packages that you made on your machine.
Yes.
And you make a new project and you use those packages. But then, because you're going to, let's say, recreate them later in life or do something else, all those folders get deleted. Now my new project is invalid. When I try to do manipulations, it'll tell me blah blah blah, packages missing, expected to be at this path. Is there
Yes.
an easy way to just automatically let it resolve, or do I have to go through and do like remove on each one of those different complaints? Is there a way to just like GC or update or something that'll just correct that situation on my machine so it just forgets about those packages that were accidentally deleted or purposely deleted?
Resolve wouldn't do that. You need to do it by hand, right?
You can pass rn dash dash all.
Yes, that's
I know, here.
that would teach everything. Yeah.
And then you just start.
Yeah.
And then you insert the install, right? So that's when you restart over.
Yeah. So you would have to remove and start over. That's Yes, go ahead.
Maybe more useful way you can do add and then just leave it get URL.
Oh yeah.
That should avoid duration because you should do the right cat. Make the maintenance on Github, and that Github is always going to be the same.
I was going to show that with this same package. So just to show an example of what Ethan just said, which is very important. So if you run into that situation, you're using local packages that are not in the registry, but they are on GitHub to facilitate and to make your environment like transferable and in a way that you can move all your dependencies with your environment, you can just add the package through the GitHub path. So for example, I can go to my own package there. Let me log in. There you go. Here. And then, okay. I have this. And I could just do, oops. I need to go here. Using pkg.add, and then I can just do this.
You are.
Yeah.
Use the BIOS mode. It's easier.
Let me clean it up. There you go. If you're in scripting mode, you can use the API. You can provide package, add, define the URL, and then you will also be able to update and add packages that are local or are not in the registry. Okay? Cool. Good question. And let me go back here. Okay. So we went over the main things that the package manager can give you. Documentation is very good, has a lot of details and more information as you go and you need to do more specialized work. Now, let's use some of the dependencies that we installed, or let's add some packages and work with some data and use functions from packages that we just added to our environment. So the first thing, let's add data frames, linear algebra, plots. We can also add statistics. So let me do, I already added, but you could do data frames. Oh, wait. And then you could do this. Yeah, you can just define multiple packages and separate them by a comma and add all the dependencies at the same time. And these are the dependencies that we are going to use. Now, oh, also CSV. There you go. Cool. So what we are going to do, we are going to download a CSV file from the micro benchmarks repository on GitHub. And this is here. So this file is called benchmarks.csv. And it has benchmarks of multiple functions and it's like timings. And you have different languages. We're going to download this file and process it using data frames and using CSV. So what we can do, you can just click here, raw, copy the link, and you can use the function download. So here I'm using Jupyter just for ease of like showing command by command, but you can do it in a .jl file, so in a Julia file or whatever you prefer, because I know that setting up Jupyter with Julia on VS Code now could take a little bit of time. So just for the sake of time, I'm going to skip that and I'm just going to show this for like ease of separating the comments. So I'm using all the dependencies: data frame, CSV, statistics, plots, and linear algebra, which we don't really need now, but it's good to have. I defined the file, so I'm just downloading the raw file, downloaded the CSV file, benchmarks.csv. And then I can use the function csv.read, and I can display it as a data frame. So csv.read, file name, data frame. There you go. You have your data frame here. Detail is the first row is going to be considered your header if you don't provide one. So you can see here that the header is C, iteration, Python, and then the timing, and then it gives you the types. But these are not like proper headers. So let's provide proper headers, right? So how do we do that? CSV, read, and then you want a data frame, and you say header, and then you say language, function, which function is being benchmarked, and then time. Very good. And this is our data frame. And now you have language, function, and time, and then type of the elements in the column. And now one thing that we'll look at, and I think Matt is going to talk more about this function, is okay, before we go there, let's just check all the functions that were tested. So if I say df data frame dot function, it gives me all the entries, all the elements in this column. So iteration Python, matrix multiply, statistics, parse integers, print a file, recursion Fibonacci, quicksort, so on and so forth. And there is a function, and that's what Matt will be talking about later. It's the user function Mandelbrot. Let's just check how Julia performed in this function. And one thing that we could do here, so we have the data frame. We know that if we do data frame dot function, we get all the entries on that column. So let's extract all the rows and all the data with respect to this function, user Mandelbrot. So this is the dot notation, which means that it's going to broadcast, and it's going to check all entries and then return the ones that are equal to user function Mandelbrot. And then the column here, it just says that it's going to return all columns that identify this statement as true. So if you use Mathematica, Wolfram Mathematica, for example, it's equivalent to all. And we have here we have extracted the data that we are interested in. So languages, function user func Mandelbrot, and the timings here. Another thing that we can do, let's now plot, right? So we imported all the functions in the package plots. So let's just make a bar plot first. So perf is the name I gave to this subsection of the data frame. So I called it perf. So perf.language, perf.time. So this would be like my x axis, and this would be my y-axis. The title of the plot, Mandelbrot performance, x label, language, y label, points. No, this is going to be time in seconds. There you go. So here's my plot, right? You can see that it's very hard to read the labels here. So what we could do, we can just do X rotation and rotate it by 45 degrees, which is going to make it much easier to read, as we can see here. So we have C, Fortran, Go, Java, JavaScript, Julia, Lua Mathematica, MATLAB, Octave, Python, R, Rust. It's it's very difficult to see the timings here because of the scale, right? So what we can express this benchmark in terms of like points per second, but then we need to go back to the benchmark and see like how many times this was done. So we can go to that code now. I actually just took a screenshot before the workshop, which would make it easier for us to just check. So if you look at MendelPerf here, you'll see that it was ran over this range, right? And we can just do the following. This range, when you check, so I need, it's 1.11 and then 2.1.5. Okay. So let's go, oops, here. So if you do range, range, let's say range A, this is 1 and then 0.1 and then 1, I guess. Here, -1. Here. Okay. And then the other range will be I still didn't memorize. Sorry. -2.1 and 0.5. Okay. -2.1 and here 0.5. Okay. What if we do range A times range B? Wait. Oh, wait. What happened? Oh, yeah, that's right. Length of each one of the ranges, and then we'll know how many points. Length. Good. Yes. So 546 points. And let's just kind of normalize by that and let's just express points per second instead of times, because I think our scale will be much easier to read. So you can see here when we do that, and again, we are broadcasting, so we are using the dot notation to apply this division to all elements of perf time. If I didn't do that, it would not work. So I need to use dot notation to broadcast. Cool. Nice. Using the same settings, so same titles, same X label and Y label, and rotating the X labels. Now we can see much more clearly, and we can see that Julia was the best performant in this benchmark for this function. And then Matt is going to talk about maybe why and explain, but that's it. And then for plotting, are we showing more plotting later? Okay. So there will be more things about plotting, but you can also look at the documentation. As you can see here, it ends up plotting with Julia. It ends up being very intuitive. You can define line plots. You can use plot, bar charts. You just use bar, and that's it. And we will be around so we can answer questions about plotting as well. Okay.
Thank you, Leticia. So that sets us up very nicely to come back, and hopefully you can kind of connect the dots between where we're going with this. Let's get rid of that. Okay. So let's go back to our walking tour and put this all together, bring it all together. Let's make this closer to the real Mandelbrot function. That's where we were going with it. That's what we were doing with the blow up count. That's actually what the Mandelbrot set is, and we'll explore this a little bit. So we had this blow up count function. I've changed it just very slightly, where we're going to now have x and some constant. Um, let's change this one more time and make that a optional positional argument here. Is that too big? That's too big. That's readable. So we'll have an optional argument, and when we do that, we actually end up defining in one fell swoop two methods at once. And it's kind of similar to how we did that promoting method, right? There was that one simple method that said, we'll take one argument and promote it to a float. This does something similar where we're going to take x and define a constant c. By default, it'll be the same. And we can do the same thing here now, where we can do blow up count of 2.5, for example. That blows up immediately because our test is over 2 again, remember, but if we do 0.26, for example, that's a little bit more interesting. Let's use some of the packages like Letícia talked about, and we can explore this a little bit better because just entering numbers in a REPL, not very helpful. We can just add the plots, right? So we can do using plots just like Letícia showed, and I haven't done that yet. Or I have, I guess. So I have that available, and so now I can just plot. One of the hard parts about programming languages in general, it's not so much the syntax as it is all the libraries that you have access to, and how do you know what you can call and how things work. And again, help is your friend. You can ask for lots of help on plots and what all is available. One of the things that you can do is you can plot a function directly. So I can just plot blow up count. And in VS Code, it'll pop up on the right here like this, and you can kind of see that it's when you give it no arguments and nothing interesting, it'll just give you a graph from -5 to 5. I can change that. It looks like something interesting is happening around 0. So I could say maybe let's go from 0 to a half. I can zoom in, right? Or maybe from 0.2 as my left axis to 0.3, right? And you can kind of see there's something interesting happening in that region for this particular graph. There's other ways that we can look at this, though. We can also look at it as an array. So we can, like I was testing lots of particular values, right? I was testing at 0.2, that hits our limit, right? But if we go to 0.27, that escapes. That eventually hits infinity. So we can test lots of individual values. We can also test a whole array of values at a single time. So like we could try 0.25, 0.26, 0.27 all at once, and that's an array. If I try this, we're going to get an error. And it's very common to see errors like this in Julia, especially no method matching errors. This was a method error, and it's telling me that, hey, I tried to do something, and it might be a little surprising, right? I didn't actually write an exponentiation when I wrote blow up count. I wrote blow up count. So why is it saying that this is happening? Well, it tells me my stack trace. It's somewhere inside here on line 6, or line 8 rather. So what's happening on line 8? Well, that's where I'm doing my x squared step, right? So it's taking x and it's trying to square it, and it's trying to square a vector, and that's not defined. So it's saying, hey, we didn't know how to take a vector. You can see the left argument was a vector, the right argument was an integer, and here it's using this shorthand. It's not even saying what the names of these things were. It just knows I was exponentiating a vector with an integer. So how could I do that? And that's where these dots come in handy. This is broadcasting, and just by putting a dot there, that is going to apply this function pointwise. And that gives me the 3 values back. And it's just saying, take this function, apply it to all the values in this array. Very powerful, very succinct. There are other ways that I could evaluate this across an array, right? I could write a for loop. I could define an array, do a bunch of things. I could, instead of writing a vector here of handwritten things, I could say, like, say, point 2 by and step by some value, point 1 to point 3 like this, 0.01 like that. Maybe if I get my syntax right, 0.01. There we go. So there you can start seeing, okay, there's maybe something interesting happening there. And of course, this is very simple with a floating point number, but it gets much more interesting with complex numbers, right? So I can start thinking about this in terms of a complex number. Well, complex numbers have two compartments or two pieces to it. There's the real part, and then there's the imaginary part. So I could have, this is where those two ranges came from. In Leticia's example, we can say from -2. So let's call these my x's. I'm going from -2 by 0.1 to 1 like this. And my y's, let's do -1 by 0.1 to 1 like that. And what I want to do is I want to create a grid. Let's do x's are my real numbers and y's are my imaginaries. Well, if y's are my imaginaries, I can multiply them by the imaginary component, and that just works. It gives me back the same, an imaginary range instead of a real range. And I can add x's to them. So if I do the same thing, right, with all of these pointwise operations, I can try this. This is not going to work. It says your arguments must match. What I want to do is I want to broadcast them out. So I don't want to just do a pointwise operation. I actually want to make this work in multiple dimensions. So there are, we've been talking about vectors. We also have matrices in the language. And we can take the vector of points and rotate it or flip it around to be a row of a matrix by just using the nice linear algebra, the tilde there. And so now my x's are no longer a vertical vector, but a horizontal row matrix. And if I add that with broadcasting to my y's times my imaginary numbers, then I get this grid, the Cartesian grid of all the points that I want to evaluate at. So now we can look at what this blow up count looks like across all of these things. Again, I want to do that pointwise as well. And I get something that looks much more interesting, right? Now we have something that you can start looking at. It's eliding things in the middle. So maybe let's make our x's a little bit smaller. And I'll use a different syntax here. Let's do a range starting at -2, going to 1 with a length of, let's say 20, maybe. Let's do 10. And same with y's. We'll do y's equal range from -1 to 1 with a length of 10. And now let's look at our blow up count. And you get this sort of image, right? Or, it's numbers still. So how would we look at this in a more interesting way? Plotting it would be one way. We can also just use colors directly. And so one way to do that is with the colors package. So we can add colors. And I've already done that, so it doesn't think that it needs to do anything. And we'll say using colors, let's pull in the color map function, and this is going to just bring in one name from this package. So there are lots of possible names that we can use, lots of possible functions that colors defines, but we'll just use color map here. And color map, what does that do? It gives me this, let's see, red, blue. Oh, what are the options here? I forget. Well, there's lots of different colors that are available to us here. A nice diverging map is the red blue. That's what I wanted. So we'll use a color map, red, blue, and grab 100 colors out of it. And when I do that, it doesn't show anything at the REPL, but instead plots it, which is interesting. We can call that our C map for now. And if I look at just what is this thing, type of C map, it is a vector of RGB things. Which is cool, right? Like we have this vector of RGBs and it plots as a gradient for us. We can look at the first value here, a C map of 1. It's a vector, so you can look at what the first value is, or we can look at the last value as a bluish thing, and somewhere in the middle, right? So like say 25, it's that pink, right? This is a vector, and we can look at all these different values. So we had our blow up count that gave us this kind of image of things. Let's change this to max iterations of 100, make it a little smaller. How could we look at this in terms of a color? Well, we just need to use these as indices, right? If you think of these as indices into our color map, we have a C map here. We can index into our color map by these things. Let's make sure our C map is the right size. So we want 101 possible values for our C map. And now if we index into this like that, we end up with a bunch of paint swatches here, right? And it's a very low resolution image, a bunch of individual kind of paint swatches. It's a matrix of paint swatches, you can think of it, a bunch of pixels. And again, still pretty low resolution. Let's add one more package here, which is the images package, add images. And now we can say using images, that pulls it in, and that teaches Julia how to display a matrix of paint swatches as a real bona fide image. So if I just rerun that exact same command, but with that, then it ends up, not plotting the spaces in between our matrix elements and just plotting it like a real image. And now I can make my X's much bigger. So let's do like 800 values this way, and our Y's are going to be 600 values that way. And we can do exactly the same command again. And now we have a nice, pretty picture. That is the Mandelbrot set. It's kind of it's a wildly simple thing, right? Just 10 lines of code. And these are almost exactly the same lines of code that we used in the performance micro benchmarks that Letícia was showing, right? Like there's no type annotations here. The one little bit of special optimization that we do is it's kind of expensive to take the absolute value of a complex number. So it's nice to take the absolute value of a square of a complex number. So there's abs2, which is just computationally more efficient. And then if you square the left-hand side of this, you'd also want to square the right-hand side. That is the function that does, outperform C in the benchmarks that we were looking at and the data frame that Letícia showed, which is very cool, right? And it's a lot of fun. So you can do all sorts of things now within this general structure. You can start playing with this a little bit, right? So you can actually start changing some of these things. There's nothing magic about this, right? It's just doing some math and asking, does it eventually blow up to infinity or does it stay at 0? And that's what defines who is in and out on the Mandelbrot set. And we just have this convention of coloring how many iterations it took to make pretty pictures. So if you change this slightly, so if you take x to the 2.1, for example, you'll get a slightly different picture. Whoops, I did not want to click there. And if I rerun my blow up count now with a different exponent, you end up with a new set. This is no longer the Mandelbrot set, but it's in the same family of sets. It's a lot of fun. I encourage you to play with this. It's 10 lines of code, and you end up with some really fun pictures and ways to look at it. Now I'm going to change gears just slightly for the last bit here and talk about compilation uh, and deployment and how you might do that. And in order to do this, we're going to go back to GitHub, and we're going to go to my repositories here because I just uploaded a repository that will give me these things. I called it Benoit and Gaston in honor of Benoit Mandelbrot and Gaston Julia, who the mathematicians for which these sets are named. And I have this repository here. This is a package, like Letícia showed. It has a source in here that has some very basic definitions that are basically what we just looked at, right? We have I called it escape in this case instead of blow up count, but it's the same 9 lines of code, right? Just asking how many times can you perform this operation without exploding up. And I have these Mandel functions, which are exactly that color map operation, looking up the color map, doing it as an operation there. And in fact, here I'm passing CMap as a keyword argument, right? So you can play around with that. What I want to do though is let's go in and let's clone this, or let's work with it. So what you can do is if you go to, yeah, let's copy this. I should have given you a short code for this, but if you go to github.com/mbauman, you should be able to find Benoit and Gaston, and you can just copy this URL from GitHub and take it back into VS Code. You could add it as a package. What I want to do is I want to clone it as a repository just so that way I can walk into it and work with it directly. We haven't talked about it, but there is a shell mode, just like there's a help mode, there's a command mode. I often use the shell mode, which is you access by typing a semicolon, and that allows me to clone this package. Now I have a folder like this called Benoit and Gaston with a manifest and a project and my source folder here. And that's all well and fine. But what I want to talk about is deployment, right? How you would deliver this to something. There are multiple ways that you might end up imagining working with this. The way I have 2 ways that we can look at it, and I put them in a bin folder. There's nothing special about the way that I named this or arranged this, but it's a convention that I've seen used before and I use. And so there are 2 things here that use these definitions, right? The definitions in Benoit and Gaston, which is just this escape function and the Mandel function, and a little bit of a step that finds an interesting region within the Mandelbrot set. So this is a kind of akin to a gradient descent, where it's looking for places where the escape function is large, and where the boundary of the Mandelbrot set is, because that's where the pretty pictures are. That's where the interesting action is. If you zoom in on the inside of the set, well, nothing escapes, nothing blows up. And if you zoom in the outside of the set, well, you explode very quickly. It's in here that the interesting stuff happens. And so this is, again, very simple Julia control flow. I'm looking at a random point, or I can take a random complex point and move it closer or farther from the origin until I find a place where I'm at a boundary point. And so that's what this is looking at here is if I make it a little bigger, you can see maybe. There we go. You can see that what I'm doing is I'm stepping in steps of a tenth and looking for a point that changes whether I'm inside of the set or outside the set. And if I'm outside the set, I want to step towards the origin. If I'm inside the set, I want to step away from the origin. And if I cross the boundary, the defaults, I found found a point where I'm no longer escaping, or I'm no longer inside, then I want to step with finer steps. So that is our way of kind of finding an interesting region. Once we have that, then we can launch a way of deploying this, right? A way of finding something interesting. And one of the cool parts about Mandelbrot sets is that there's a complement of the Julia set, which does effectively the same thing, but holds C constant instead of looking at lots of potential C's. So it's a slightly different way of formulating your escape function. I know I'm going over this quickly here because I want to get to the point where I deploy this out. And so how do we deploy this? Potentially to a web uh, uh, setting. One way to do it on the web is by using dash.jl, which is a product written in JavaScript, really targeted towards Python, but works great in Julia as well. You can bring that in using the dash function, dash package. And what I'm going to do is I'll just have a very simple app. You write your HTML, it's a web thing. So I have a HTML and I have a button that will give me a random point, find an interesting place in that, and give me the Julia set at that point. So let's do that. Let's look at what it looks like to run that. What I'm going to do here is I will go into my Benoit and Gaston file here, and I will just run Julia with a project flag. So this is very common when you're deploying Julia. We have the manifest and the projects that Letícia talked about. We know what they are, what dependencies are required to run this. So I'm going to say the project is this current folder because I'm in my Benoit and Gaston folder. And we can then run bin/web.jl. This will compile everything and launch a web server. There we go. We have a web server that I can go to my web browser now. And we have hello JuliaCon. And every time I click go, I will pick a random point, do that descent operation, and give myself a pretty Julia set picture. That is a fun way of doing it. So that's one way of deployment. It's very straightforward, very simple, and you could imagine a much more complicated thing than a single button here. You could imagine exploring the Julia set and having all sorts of fun ways of doing this, but this works great and is a fun way. And you can see the complex point about which the Julia set is being generated. But one of the most exciting things that's happening this year at JuliaCon is static compilation. So how would you create an executable that does this? And that is now available. So this is now us jumping up to the 40th floor of the Cathedral of Learning. Let us, instead of launching Julia to run some web server, we'll cancel out of this. And let's instead compile this. So in order to compile this, I've been using Julia 1.11. Many of you have been been using Julia 1.10. I need to use the new beta Julia to do this. And in order to do that, we'll use Julia up. And we can ask what the Julia up status is. I have a bunch of Julias installed on my computer because I've test everything. But what I want to do is I want to look at the beta release, the RC1 of version 1.12, which includes the ability to create executables. So let's do that. Let's do Julia plus beta gives me the Julia version 1.12. And now there's one tricky part here that in order to compile this to an executable, we need to run Julia C. We need to run a compiling script that does this. And the Julia C script right now is pretty hidden away. Let me find that here. Let's go back here. Julia C. So we will use the current project, and it uses a Julia C driver script that's hidden away in the Julia beta release. This is going to get standardized more. And we just say output exe, let's call it Gaston, and use source/cli.jl. So whereas when I was doing the web thing, I was looking at or bin/web, I'm going to look at bin/cli. And all that this does is, let's hide that, takes a command line argument. It has this special main entry point. We know that the arguments are going to be a bunch of strings that we get from the command line, and it's going to return in a C integer. And we'll just run some Julia set at a random point and create a ping out of that. So let's do that. Let's do that. I labeled this. This is going to be our bin. And this is kind of like calling GCC. This is saying, hey, I want to output some executable. It'll compile it. It'll take some time. And I think if I did this correctly, we'll end up with a executable at the end. It is slow. It's doing all of the compilation. It's actually compiling all of Julia itself into this. And so it's going to give me a very large executable as well. We'll see how big that is in just a moment. But it's going to give me something that I can run from a command line that doesn't need to dynamically load packages, doesn't need to dynamically run a script that I have. It's going to be a compiled executable for me, I hope. It is similar to system images. It's using the same infrastructure, except now instead of output, so you may be familiar with the output sysimage option to the Julia command line. This is going to output an exe now instead. And I think I did that right. It didn't take this long when I did it last night. Maybe I did something wrong. Yeah, that's the problem. Doing dangerous things with beta releases live is always interesting.
You're saying this will be like a couple hundred bay?
That's right. So this is including all of the packages, all of the functionality, including things that I don't use. So there we go. We ended up with it. We can look at what it is here. So we have this Gaston, and I can run /Gaston here like that, and it will give me a ping back out. And there we go. We have a random image. I can run it again. It'll re-update. And it runs really quickly, right? It doesn't have much startup time there, but it is big. And if I look at ls-lh, we are looking at 200 megabytes. So that's where the magic in the beta version comes. We have this new experimental trim unsafe. We'll just throw away everything that Julia can prove is not available to it. Oops, I did that in the wrong order. I need to go here. Experimental trim equals, so trim, it will remove everything that Julia doesn't think you'll need. And that's all based on, if there's any dynamic calls or anything like that, Julia isn't able to predict what functionality you will need. So this will even remove out the compiler. It strips away everything that it doesn't think you need. The unsafe here is saying, there might be some functionality that it can't prove that it doesn't need, and it will throw that away too. And it'll just error if it runs into those things. And now I can do the exact same thing. So let's run Gaston again. We'll update my image. It's working very nicely. But now the magic is that this is only 2 megabytes instead of 200 megabytes.
Can you do that with system images? That trim concept?
It's not as obviously applicable to a system image. So the question is, can we do this exact same trimming with a system image? A system image, so this is built on the idea of where Julia came from. So when you run Julia itself, it's running compiled code where did that compiled code come from and where does that compiled code live? That lives in what's called a system image that has a lot of the infrastructure that we think that you will need when you're running Julia. That's why Julia itself is big. And so when we ran Gaston, or when we compiled it without the trim arguments, it's effectively doing the entire system image. It's effectively grabbing all of Julia, putting it together. And the reason for a system image, you can also compile your own custom system images that include more than just the base functionality. You can include things from other packages, data frames, plots, all sorts of things. People do this regularly, and it works quite well because it's common functionality. When you trim though, you're saying I want to throw away everything that I didn't use, and system images are typically used in an interactive context, so you don't know what you're going to use. And so you could trim a system image, but you'd end up with nothing because you don't know what the person's going to end up using. You don't have the concept. What's different here is we have the concept of an entry point. That's what the main macro does. And that's where Julia starts its tracing to figure out what it doesn't need. So anything that these things don't call gets thrown away. If I were to remove some things here, it would become smaller. If I just made this into a print hello world, it would be very small because it doesn't compile anything. Or it just compiles the output statement. If I added more things here, this would get more complicated. Yeah. Yeah, go ahead. Oh, that's a good question. Like, I am not well versed with LD and how the linking commands work. I did get things out here. Like, it is linking to LJulia. LDD. Capital L. Yeah, there you go. So yeah, there is a libjulia dependency here. Yeah. Yeah, so the question is, why is this exciting? Why do we care? Why do we want this to be? And it might not be. It kind of depends on your use case. For uh, you know, a person who's doing scientific investigations and using Julia as a full-fledged environment to do exploratory analyses or things like that, you may not see it or may not want it. But for someone who is uh, building a tool that you want to end up using, the static compilation ends up uh, doing all of the work that you, or the all those little lags that you end up seeing in Julia, that first time to plot sort of thing, does it all up front for you. And so you do that, pay that cost once, and then you have a compiled tool at the end. The big thing that it'll actually unlock is once we start talking about cross compilation. So this just compiled for my Mac and my architecture and is very specific here. The next step will be to be able to cross compile. So that way on my Mac, I can compile to a different computer architecture and ship a windows.exe. That is not currently easy or possible, but definitely something that would be nice to have. And then you can start thinking about shipping applications, right, that are built with Julia. The other really powerful thing here is that these can not just generate EXEs, but they can also generate DLLs or shared libraries that then you could ship alongside another language or as a backend tool component to a C# application or something else that you're working on. Yeah. Yeah. Go ahead. Yes. Yes. Generally, yes. There are correct. Everything that gets saved, you generally see some things. So like when we were loading packages, you saw pre-compiling. That is saving a effectively a package image. It's kind of like a system image for that package. It's doing all of that pre-compile work. And there are ways that you can teach packages to specifically compile particular workflows. So that way they will generate the native code that you know that your users will probably have. That's generally the best way to cache that sort of thing is by creating a real package, having a pre-compile workflow that then, compiles all of those things together. And then it's saved as part of the package, package precompile files, and happens when you on install time of the package itself. And then every time you use the package thereafter, you don't see that precompiling step again, as long as you don't update. And so that's the place that you'll cache it. The things that you define yourself in a script or even a package that you've not written a precompile statement for, those will always, every time you stop Julia and restart it, you'll pay that cost. But good question. Yep.